Hello, everybody. So today what we're going to be looking at is section 2.3 in your book, which is going to be the dot product. So I'm pretty happy that we're to this point now, just because the previous sections covered so many different things, right? Like we had what is a vector, scalar multiplication, addition, subtraction. What's a sphere look like? What's a cylinder look like? Oh no, I didn't do a cylinder in the last lecture. Uh-oh. Stuff like that. So anyway, this section is just about the dot product, so it's definitely a lot more focused. Okay, so hopefully that will mean a shorter lecture for us as well. So let's talk about the dot product. So first of all, you learned in previous sections how to add and subtract vectors, right? How to add and subtract vectors. I'll say two vectors, right? And you learned scalar multiplication. So you learned how to multiply a vector by a number. But what you didn't learn is how to multiply a vector by a vector. And that's what we're going to learn today. Oops. So you learned how to multiply a vector by a scalar number. So the question is, how do you multiply a vector by a vector? And the answer to that is that there's more than one way to define it, and it could be used for various, each way that you can define a multiplication between a vector and a vector can be used for different applications. Okay, so there's more than one way to do it. So there are a few ways to do it. I mean, technically, there'd be infinite number of ways if you let people do whatever they wanted, but there's a few ways that we care about how to do it. So there's two ways to do it. We will learn the dot product today, and in the next lecture, we're going to learn how to do a cross product. Okay, and again, what I already said is true. These have different uses, and that's why we define them. So like a dot product, you write this way with a dot, and a cross product we write with the other way that you've used in your life for multiplication, with a cross. So obviously the names make sense, right? Dot product, dot, cross product, cross. Okay, and those are our two ways that we're going to learn about how to multiply a vector by a vector. Okay, and like I said, they have different uses, and today we're going to learn about the dot product. So today, dot product. So let's talk about it. So what is it? So we can define it for a three-dimensional vector and a three-dimensional vector. So definition, the dot product of a vector u, which we're going to call u1, u2, u3, and v, which is going to be v1, v2, v3, is given by this formula. So here's our formula. So we write it u dot v, right? That's why it's called a dot product. And the way you calculate it is you multiply the components. So u1 times v1, u2 times v2, u3 times v3, and then you add those all up. So you go u1, v1, plus u2 v2 plus u3 v3. And that's your definition. Okay. So that's what a dot product is. I'm going to put a box around that so you can find it easier if you're looking later on. All right. So that's your dot. Now you can also do this in 2 dimensions. You would just leave off the u3, v3. So maybe I'll make a little note there. In 2D, it's u dot v is going to be simply u1 v1 plus u2 v2 like that, and there's no u3 v3. So no big deal. You can do it for 2D or 3D. It's actually important that we make this distinction, though, that this one's okay, because when you're learning about the cross product, there is no cross product for 2-dimensional vectors, and there's no obvious way to extend it to 4-dimensional vectors. So the cross product only makes sense for 3-dimensional vectors, 3 components. Whereas the dot product, it really doesn't matter, 2, 3, 4, 5, 6, 7, 8. It's obvious how to do this if you had, 5 components, right? You would just keep going, u4, v4, u5, v5, and so on forever. So the dot product can be extended easily to different numbers of dimensions, but the cross product, when we see it, we'll learn that that's not the case. Anyway, so that's the definition of a dot product. So before we talk about what we're going to use it for, let's just make sure we can calculate it. That should be easy. It's a very simple operation, which is nice. So example here, find u dot v if u is 3, 5, 2, and let's say v is -1, 3, 0. Okay, and then how would I do that? So the way I would do that is simply like this, right? So u dot v is equal to, I'll write it out, 3, 5, 2 dot -1, 3, 0. So I'll usually write it out like that so I can see the numbers next to each other. And then from there, then we'll actually perform the operation. So you're multiplying, oops, I erased it. You'll multiply first component times first component. So 3, -1 plus second component. So 5 times 3 plus third component. So 2 and 0. So what do we get? We get -3 plus 15 plus 0. And overall, you get 12. All right. So something you want to pick up on very quickly here is that your answer for a dot product is a single number, right? So we didn't mention it up here, but this is a vector, this is a vector, this is a number, right? So the result of a dot product is a single scalar number, right? The result is a real number. Actually, I think the way they say it is scalar, but a real number. So the result is a scalar. Okay. And because of that, also some people refer to a dot product as the scalar product. Since the result is a number, some people call the dot product the scalar product. Now, probably you're not going to see that in your homework, but still, you may see it somewhere in the future. And if you do, that's what it is. Scalar product is the dot product. So, hopefully you can see that today's lecture is not going to be so bad, right? Because all we're learning about is the dot product, and the dot product is very easy to calculate. So just basic arithmetic is all you need. Calculate a dot product. All right, now let's talk about properties of the dot product, right? Because we have to learn how it works. Now, part of the reason, well, not part of the reason we call this multiplication, right? So like this operation here is not regular multiplication. So if it's not regular multiplication, why are we using the word product, right? Dot product, cross product. Product means multiplication. And the reason we call these products is because the operations obey some of the laws of multiplication in real numbers, right? Like, how multiplication works, right? Like if you multiply something by 1, you get the same thing back, right? That's a product that multiplication has in real numbers. Now, this is not going to have that product because there's not going to be anything, right? You can't multiply u by anything and get u back because the result is a scalar. So that particular property of multiplication of real numbers could not possibly apply here, right? But maybe there are some other properties that this has that, do apply. Maybe it acts like regular multiplication in some way. But what properties it has and what properties it does not have, we need to list so we know what they are. Okay, so here's the properties of the dot product. Properties of the dot product. So there's 4 that we care about here. So the first property is that if you do u dot v, you get the same answer as if you do v dot u. That's a property. And that's a property that regular multiplication has. Regular multiplication is commutative, as we say. Just means the order doesn't matter. Now, the second property that we care about is going to be a distributed property. So if you do u dot v plus w, so all of those are vectors, and we have, if we have the parentheses here on the v and the w, and then we're going to do the dot product with that result, turns out that you can take this u and distribute it across the v and the w. It will look like this: u dot v plus u dot z u dot w, like that. So that's just a regular distributive property, right? Like this times this times this. The only difference compared to the distributive property for real numbers is that our multiplication is a dot product. Otherwise, this looks normal, right? So that's a property that multiplication has, and also dot product has. Distributive property. We can be more elaborate there, and we could say that the dot product distributes across a sum, but we'll just say distributive property. What other property do we have? Well, turns out that if you have a constant, so no arrow over the top, so this is a constant, it's a scalar number, and then you do a u dot v, turns out that that's the same as if you multiply the c times the u first, and then do the dot product with v. And it's also the same as if you did u dot cv. So it doesn't matter whether you multiply the c after you do the dot product, or if you multiply the c by the u, or if you multiply the c by the v. You can do it any way you want, and the result will come up the same. And so what's that? That's an associative property, because basically we're saying we can put the parentheses where we want for that multiplication. At least that's what they call it here. Associative property. And the last property here, it's not really got a name, but it turns out that if you do v dot v, so a vector times itself, it turns out that the result is the magnitude squared. Okay, now this is not any complicated thing here. Okay, like if you look at that and you're like your mind is blown, you're like, what? Why is that the case? Well, it really shouldn't confuse you, right? Because remember that the magnitude of v by definition was this, um, like uh, x1 squared plus x2 squared plus x3 squared when we were, or no, we called them x, y, and z. I don't know what I just did there. X. Why do we need ones and twos? Sorry. Didn't know what letters I wanted to use there. Uh, we know that the magnitude of a vector was like the x component squared plus the y component squared plus the z component squared, right? And if you do the dot product of a vector with itself, right, it would be like x1 plus x, doing it again, y1 plus z1, right? So of course this is this, just without the square root. So that's why it is the way it is. So this is a pretty simple idea here. It's not really like a theorem or anything. It's just noticing this, like that this magnitude is this, and that this is actually the dot product of the vector with itself, and then a square root. So that property gets used a lot though. So you're going to need to understand that property. Okay. So I don't know which of these we're going to prove. I mean, there's not really a lot to prove on any of these. So if you wanted to, let's just pick maybe one to prove here. Well, neither one of them is very hard. Let's prove number 2, which I just called number 2 like this. So number 2 proof. So what was number 2? It was this, right? So number 2, we started with u dot v plus w. So u dot v plus w like that. And so I'm going to assume that like u is u1, u2, u3, v is v1, v2, v3, w is w1, w2, w3. So if we write this out, right, this is, I guess by definition, u1, u2, u3, dot, v1, v2, v3, triangle brackets, plus w1, w2, w3. So that's how I'm going to write them. Now, if we're doing this in order according to the parentheses, I need to add these two things together. So we get u1, u2, u3 dot. Add these up. I guess I don't need parentheses now because I'm going to add them. So you end up with v1 plus w1, v2 plus w2, v3 plus w3, like that. Then you do your dot product. So you're going to multiply first components together. So you end up with u1, v1 plus w1 plus u2, v2 plus w2 plus u3, v3 plus w3, like that. Then now that I can have this, I can just multiply this out. So we can use the distributive property for regular numbers now, right? Distribute the u on the v and the w. So we were trying to basically prove the distributive property for vectors, and it's going to boil down to the fact that real numbers have the distributive property. So we apply our distributive property here. We get u1 v1 plus u1 w1 plus u2 v2 plus u2 w2 plus u3 v3 plus u3 w3. So just multiply everything out. Then what you can do is collect all the w's first. There's 3 terms with w's, right? Or sorry, 3 terms with v's. This has got a v, this has got a v, this has got a v. And then 3 terms with w's, w, w, w. So write the V's, then write the W's. So you go U1 V1 plus U2 V2. That's this one. And then U3 plus V3. Sorry, U3 V3. Right? Those three. And then three of the terms have W's. U1 W1, U2 W2, U3 W3, like that. And then if you look at this result, you can see that this right here, this entire thing that I put in parentheses, this is the dot product of U and V, right? U1 V1, U2 V2, U3 V3, that's the dot product of U and V by definition. So this is U dot V. And this one right here, obviously U1 V W1, U2 W2, U3 W3, that's the dot product of U and W. Like that. So if you look at what we did here, just all at once, we just showed that U dot V plus W is U dot V plus U dot W. That was that second property. And, it was distributive property for vectors, and it just relied on the fact that individually each of these three things, which were all real numbers, had their own distributive property of real numbers here, here, and here 3 times. That's what it boils down to, but we go through the process and we see that, yeah, the formula is true. And so you can do that similarly for each of the others up here if you wanted. And they're pretty similar. It's just the real numbers have certain properties, and so it turns out that the vectors have these properties as well. If you write it out component by component, you can see where you have to use the property for real numbers. Okay, so that's a property. I think I don't really want to use any of those properties right now. You can practice it in the homework, right? I mean, it's not that hard or easy. Here's a big property that's important. So angle between vectors. Angle between vectors. So I've been trying to debate whether or not I wanted to prove this or just write it. And I think I just want to write it. I'm realizing that I never saw it proved when I took this class. So maybe we don't want to waste the time. I don't know. But here's the property. So it turns out that here's an important dot product property. Which we should have written up with the other ones, but they didn't when they wrote it in the book, so I didn't either. It's okay, it'll stand out more here. So important dot product property. So U dot V, it turns out that there's another way to calculate it, other than the one that we showed you already. It turns out that the way you can calculate it is with the magnitude of U times the magnitude of V times the cosine of theta, where theta is the angle between the vectors. And yeah, the angle between the vectors. Okay. So the proof is a little bit complicated for this because it involves using like the law of cosines and a bunch of algebra. It's in the book though, so you can look at it if you want. So the proof uses the law of cosines. You end up drawing a triangle and measuring the sides of a triangle. That's what these are from. They're the sides of a triangle. And the sides of the triangle are related to the cosine of an angle. And when you write it with the law of cosines, then that's where it comes from. But the proof uses the law of cosines plus some algebra. It's in the book if you want it. So this is a very important property though, because you can use it to calculate the dot product, right? Because it's a formula for the dot product. Um, but also you can use this formula to work backwards and to find the angle theta. If you knew everything else, you could find the angle theta. Okay, so that's kind of the two ways we use it. So you can use this to, number one, compute the dot product in a different way. If you happen to know the angle theta, if you happen to know theta, or if you don't know theta, maybe you can use the formula to actually solve for theta using algebra. You can actually use it to find the angle theta between two vectors. Now, why would you want to do this? Well, there's different problems. Like you might have information given to you in such a way that this is just the easiest way or even the only way to actually solve for the dot product. So like if I do an example here, if I draw a picture, right? If I give you a picture like this, and I just say like, here's a vector, and I tell you that its length is 5, right? And here's another vector, and let's just say I tell you that that vector's length is 8. And then let's say I tell you that this angle happens to be 30 degrees, right? I can say, find the dot product of these two vectors, and I gave you enough information, right? Find the dot product. I'm going to say of u and v, and then I'm going to write that on the graph. Right, so this is u, and this is v. So find the dot product of u and v. And it turns out that you can't do it without this formula, right? Like, how are you going to use this formula here? Right? In order to use this formula, you have to have the components, right? The x, y, and z components. And if I just draw a simple picture like this, I didn't tell you the components. I didn't tell you the components. I just told you the length is 5 and the length is 8. And this angle is 30. So I purposefully didn't give you the components. So you're kind of stuck using this formula, aren't you? Right? Because that's just what I gave you for information. So that's where one place where you might use this formula. So we'll use that u dot v happens to be magnitude u, magnitude v, times the cosine of the angle between them. And then you just fill in the numbers, right? So the magnitude of u is 5 because I said so and labeled it on the graph. The magnitude of v is 8 because I said so and I labeled it on the graph. And the cosine of theta, well, it's the cosine of 30 degrees. Why? Because I labeled it on the graph. So you work this out, that's 40. You work out the cosine of 30 degrees. Use a calculator if you have to. Cosine of 30 degrees, right, is square root 3 over 2. So overall, the result is 20 square root 3. That's the dot product between them. Right? So it's just, you could think of it just as an alternate way to find the dot product, okay? However, you could also use it to find the angle, right? So I'm going to need calculator here. I'm trying to think, where's my calculator? This is going to be like 1 second while I walk across the room. Sorry about that. All right, sorry for the wait. I got this. I picked up a graphing calculator, a nice pink graphing calculator on eBay for I think $13. Pretty good deal, and it does fractions and square roots and all that stuff. So that's nice. All right, so let's calculate the angle between vectors now. So example. So I'm going to say find the angle between two vectors here. What are they? 2, 5, 6, and also -2, -4, 4. All right, so we're going to find the angle between those two vectors. Okay, and so the way you do it is you've got this original formula, right? So we know this, that u dot v is equal to magnitude u, magnitude v, cosine theta, right? But that means that the cosine of theta, of course, is u dot v, just rearranging this over magnitude u, magnitude v, like that. So what you're going to do is you're basically just going to calculate that left-hand side first, and then we'll solve for it using like an inverse trig function here. So figure out this left-hand side. That's what we're going to do. So first of all, we're going to need the dot product of u and v. So let's just figure these out. U dot v is 256 dot -2, -4, +4. Right? So 2, -2 plus 5, -4 plus 6, 4. So we have -4 minus 20 plus 24. Oh, is that going to be 0? Is that 0? Okay. Did I do that right? Hold on. No, I didn't, because, wait, did I write these correctly? Hold on. Hold on a second. Give me a second here. -4. Okay. -20. Got it. +24. Oh man, that's 0. That's 0. Okay. That's not really what I wanted here, but that's what happened. So that's what happened. I'm going to pretend that that's not 0 and keep going. Okay. So that's the dot product, happens to be 0. Let's calculate the magnitude of u, because normally you would need that. So the magnitude of the vector 256. Now, the reason I'm saying I'm calculating this, even though this came up 0 on the previous step, is because if you think about filling this out here, we just calculated u dot v, which is in the top. If the top's 0, this entire fraction is 0, which means there's no real reason to calculate the magnitude of u or the magnitude of v. This entire thing is 0. That's why I said I'm going to ignore that this is 0 and just keep going, because normally you would be calculating this in order to solve this problem, right? So magnitude u is going to be square root 2 squared plus 5 squared plus 6 squared. That's why I like to have a calculator here, so I can just punch this in. 2 squared plus 5 squared plus 6 squared, 65, square root 65. Do the same thing for the magnitude of v. Magnitude, what is it? -2, -4, 4. So that's going to be square root 2 squared plus 4 squared plus 4 squared. I'm being lazy there. I'm not writing any negatives because I know that when you square things, you just make everything positive anyway. So I'm just sort of saving time. All right, so the inside there works out to 36. So that's square root 36, which is 6. And we got those magnitudes. And then what we can do is we can write out our formula. So using the formula, just going to copy paste it. Hold on. Duplicate. Come down here. Oop, not that far. So this is your formula. It's going to become, on the top, you've got your u dot v, which was 0. On your bottom, you've got square root 65 times 6. All of that is equal to cosine theta, right? So in this case, it's just 0 equals cosine theta. And normally what you would do here is you're trying to find theta, so you would do an inverse cosine on both sides normally. So apply cosine inverse to both sides, right? So you have a cosine inverse of, in this case, 0 and cosine theta. And what you get is on the right-hand side there, those cancel and you just get theta. And on the left-hand side, you get cosine inverse theta, which, what is cosine inverse? What's cosine inverse 0, right? Cosine of what is 0? And you get pi over 2, right? And so you punch that into a calculator and that's what it will tell you. So that is your answer. So the angle between the vectors, they're 90 degrees apart, or pi over 2 radians. So the vectors, u and v, are 90 degrees or pi over 2 radians apart. That's the angle. Okay, so that's the deal. Normally, again, you're actually going to have something other than 0 here, and that's fine, right? Like whatever number you have here, you just do the cosine inverse of it and you're going to get an angle, and that's the angle that you want. So put it in radian mode if you want your answer in radians, and put it in degree mode if you want your answer in degrees. All right. So let's see here. Okay. So there's kind of some shortcuts to these angles as well. So using the properties of the cosine, it can be shown this property. So using knowledge, I won't say properties, but knowledge of the cosine. And what I mean by this is, like, you know that cosine of 0 is 1, right? And like cosine of, pi over 2 is square root 2 over 2. And cosine of, what I say? I don't know what I just said. Cosine of pi over 4 is square root 2 over 2, and square root, and cosine of pi over 2 is 0. And basically what you can do is, using the values of the cosine that you can come up with these simple properties that, for two vectors, u and v, right? What we're going to have, the angle theta is going to be, where is it? What is the information I'm looking for? Hold on. If if 0 is less than cosine theta less than 1, then theta is acute, right? Between 0 and 90 degrees. If theta is in between -1 and 0, then theta is obtuse, right? Um, if cosine theta equals 0, we just saw what happens if cosine theta equals 0, then theta is 90 degrees or pi over 2, right angle, right? Pi over 2 radians, a right angle. And if the cosine of theta equals -1, then what? Straight. Then theta is 180 degrees. That's what we call a straight angle. Is there anything we're missing? If cosine theta is +1, then theta equals 0. The vectors have the same direction. Okay, so you can just tell different stuff from the value of the cosine. You still have to calculate a lot just to get the value of the cosine though, right? Like you have to calculate all this to get the value of the cosine, and in which case you may as well just do this last step and actually find out exactly what the angle is yourself, right? So I don't really know how much effort this saves you knowing these, but they list them out in the book, so I listed them here. Okay, now I'm going to write this as a definition, this thing, just because it's going to be maybe possibly your first exposure to this word here. You know the word perpendicular, right? Right angles, but you may or may not know the word orthogonal, which means the same thing. So what we say is, let's see, the non-zero vectors u and v are orthogonal, and orthogonal just means the angle between them is 90 degrees. If and only if u dot v equals 0. Okay, so that's actually how you check if two things are orthogonal. Orthogonal just means perpendicular. Okay, so yeah, that's it pretty much. So back up here, right? As soon as this dot product came up 0, I knew that the angle was 90 degrees between them. But, I just continued on with the problem because we didn't know as a class. But now we do. So dot product is 0 means angle 90 degrees. Now there is that one caveat there. Angle is 90 degrees, but only if they're non-zero vectors, right? Because if you do the dot product of a vector with 0, like 0, 0, 0, obviously you're going to get 0. But that doesn't mean that the angle between them is 90 degrees. That's why they say non-zero vectors here. Okay, so they'll ask you if vectors are orthogonal sometimes, and this is what they want you to do to check it, right? So they'll say something like this, like example. R P, which is 105, and Q, which is the vector 10, 3, -2, orthogonal, right? And so what do you have to do? First of all, remember that orthogonal means 90 degrees, but also you know that the way to check it is to check that the dot product is 0. So check if dot product is 0. So that's really easy to check. So you just go P dot Q, follow the rules. It's going to be 1 times 10, that's first component, 0 times 3, that's the second component, plus 5 times -2, that's the third component. So that's 10 plus 0 minus 10. So the result is 0, right? So what's our answer? The answer is yes, they are orthogonal. They are orthogonal. So P and Q are orthogonal. Easy as that. Okay, so the angle between them is 90 degrees. And we didn't actually have to do, like, you didn't have to calculate like the magnitude of them or anything, because to tell if the top is 0, angle's automatically 90 degrees, you don't need to actually calculate this magnitude or this magnitude. That's why you don't go back to this formula to calculate if they're orthogonal. You just need the dot product. You don't care about their length, because if the dot product's 0, the whole fraction's 0. Okay, hopefully that makes sense. Another question they like, I think they do this in the homework, so I'll do one example of this as well, is they give you two vectors, but they give you a variable in one of them. So they say like, for what, let's say A, R, U, which is a vector, let's just say 3A2, and V, which is also a vector, let's just say -4 for -1, orthogonal. Right? For what A are these two vectors orthogonal? And so what they're saying is, how do you make that dot product 0, right? That's what they're asking, right? So what they're saying is figure out which A, value of A, makes the dot product 0. So if you understand that, then the problem's not that hard at all, right? Because you just go like this. You just go, u dot v is supposed to be 0. So then you do u dot v, right? So first component's 3 and -4. So you go 3, -4, plus second component, which is a and 4. Oops, that's a highlighter. A 4. Third component, which is 2 and -1. 2, -1 equals 0, like that. And then you just solve for A, right? That's all you have to do now, just with algebra. So you have -12 plus 4A minus 2 equals 0. So that looks like 4A minus 14 equals 0. So that looks like 4A equals 14. So that looks like A is 14 over 4, which is 7 over 2. That's the value. So A equals 7 over 2 will make the vectors, what are they? U and V orthogonal. Okay, so that's just understanding that property. Dot product is 0. Okay, let's see here. So what? Okay. So I'm gonna do this because this is something that I forgot to do in the previous lecture, and so doing this now will make up for that. But also, I don't think it's on the homework. So let's see here. I'm going to talk about what are they called? Standard unit vectors again. We talked about this in the first lecture, but not the second lecture, and we kind of needed to in the second lecture a little bit. So standard unit vectors. In 3D. And this is why we need to talk about it, because we only talked about it in 2D. So these are definitions. So the vector I, now you might remember this from the first lecture where I said I was 1, 0. That's true. But in 3D, you have to add 1, 0, 0, right? Because we need 3 dimensions. And also in the first lecture, I said that the vector j was 0, 1. That's true, but in 3 dimensions, what is it? Well, again, you have to add the third one on the list. And then if you're in 3 dimensions, well, we got a 1 in the first spot, we got a 1 in the second spot. What about the third spot? That's k. 0, 0, 1. Okay, so I, j, and k are the standard unit vectors. So there's 3 of them in 3D instead of 2 of them. So these are the standard unit vectors in 3D. What do they look like? Well, I mean, it's pretty easy to understand that. If you look at a set of axes, like this, you got z here, x, y, right? And then your standard unit vectors are simply like this one pointing straight up. That's pointing in the direction of z. So that must be the vector k. And then you've got one that points in the direction of y. That's the one that we call j. And then you've got a third one that points in the direction of x. And that's the one we called I. So I, j, and k. So they just point in the direction of the axes, right? So I, j, k for x, y, z. Standard unit vectors. And so what you can do with that is, well, first of all, you can write your vectors in terms of the standard unit vectors. So a vector like this, for example, let's say just like 3 minus 5, 7, right? Can also be written as, we call it, let me give that a name. So let's call it like u or something. You could also write that vector u as 3i minus 5j plus 7k, right? Because I is in the direction of x, so 3i is 3, 0, 0. J is in the direction of y, j is 0, 1, 0. So negative 5 times 0, 1, 0 is 0, negative 5, 0. And 7k is 0, 0, 7. Right? So you can write it this way, 3, negative 5, 7, or 3i minus 5j plus 7k. And these are just alternate notations for the same thing. Now, what are we doing with that? Well, the reason you might see it in this section is just because they have what they call the direction cosines and the direction angles. So in this section 2.2, sorry, whatever we are, 2.3 has the concept of direction angles and direction cosines. Now, what are those? So the direction angles are the angles that a vector makes with the I, the j, and the k. So there's three of them. The angles, I'll say alpha, beta, gamma, that a vector makes with the x-axis, y-axis, and z-axis. Okay, so what's that look like? Well, let me take this picture here. So duplicate it, move it down. I don't know. Actually, I guess I can't use very much of this. I thought I was okay. Well, that was just a waste. Um, okay. Okay. So like if you've got a vector in space, so like starts at the origin and then it points up like that, and like let's say this is the vector v. Okay. So there's three angles that you could measure here. I mean, there's a lot more than three angles, but the three that we care about are going to be, well, you can measure one angle from the vector to this x, and that could be alpha. And you could also measure an angle from v to the y-axis, this one, and that would be what they call beta. And then you could also measure an angle from v to the z-axis, and that would be gamma. So those three angles are what they would call the direction angles. Now you can also do the direction cosines, which be the cosines of those angles. So the direction cosines are, they're simply going to be cosine alpha, cosine beta, cosine gamma, right? And the way you would calculate them, either the direction angles or the direction cosines, is by using the I, j, k vector, right? That's how you would do it. So you compute them, the angles or cosines, using the I, the j, and the k vectors. I don't really want to do like a whole example just because I left it off the homework. But like, for example, so if I wanted to find the direction cosines of, and I have v, and let's just give it 2, 3, 3, something like that. What you would do is for alpha, right, the angle with the x-axis, right? What you would use is you would simply use sorry, brain fart. What are we doing? Oh yeah, the dot product of v and I, right? That's the vector in the direction of the x-axis is I, and that would equal magnitude v magnitude I times the cosine of the angle between them, which is alpha, right? And then you would actually have to calculate this. So if you filled in the stuff, right, v is 233 dot I, which is 100, equals the magnitude of v, which is 233, the magnitude of I, which is 1, 0, 0, and then cosine alpha. Now, the thing about this is that this actually simplifies a lot when you go to try to calculate this, right? Because this dot product here is going to be 2 times 1, and then 3 times 0, 3 times 0. So you calculate all this, and this side just works out to 2. And then on the other side, you've got this magnitude of v, which you have to calculate, right? Magnitude of v. So 2 squared, 3 squared, 3 squared, right? But the other one, the magnitude of 1, 0, 0, the I, j, and k, the length of them is obviously 1, right? Because there's only one number here, right? The others are 0. So the length of 1, 0, 0 is simply 1. So you have that, and then you have 1, and then you have cosine alpha. So you have like 2 equals, what is that? Square root 4 plus 9 plus 9. So 9 and 9 is 18, 18 and 4, so it's just square root 22. Right? So cosine alpha is 2 over square root 22. Right? And you have that. And you could do the same thing for the beta and the gamma, but it wouldn't be I, it would be j and k. Right? So for beta or gamma, do the same thing, but use the j and k instead of I. All right. So that's something you can do, and that's not on the homework. But I did it just because I wanted to mention the like the standard unit vectors stuff. Okay. So let's see. We are 1 hour and 2 minutes in. I could do another lecture on this. Trying to think here. You know what? I think I am actually. So the next thing we have to do is vector projections, but they take enough time. I think that we'll do them in another video, a shorter video. So so vector projections are in the next video. In the part 2 video. Okay. So that's it for now. I'm going to film another video tomorrow, so you're going to get 2 tomorrow, I think. All right. I will talk to you then.